Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. Lecture 15-2. Vertical Design Seismic Force. In ground motion, there are three components. They are east-west direction, north-south direction, and vertical direction. From the east-west components and north-south component of the ground motion, horizontal seismic force is induced. And vertical seismic force is induced by the vertical component of the ground motion. In this lecture, we will talk about the vertical design seismic force. That's the seismic force in the vertical component for the design of the structures. And here are some terminologies. Vertical seismic force. In Chinese, 垂直地震力. There's the vertical component of the seismic force for the design of the structures. Vertical seismic force of beam and slab. In Chinese, 梁与楼板之垂直地震力. Vertical seismic force of column. In Chinese, 柱之垂直地震力. Because the fundamental vibration frequency of the vertical component of the beam and slab is different from that of the column. Therefore, the vertical seismic force of beam and slab is different from that of the column, so that they are considered separately. Vertical spectral acceleration, in Chinese, 垂直设计普加速度. In addition to horizontal component of the spectral acceleration, there is vertical component for the spectral acceleration. The last one, vertical seismic force reduction factor. In Chinese, 垂直设计地震力之折减因子. The reduction factor is due to the ductility of the structures. According to Seismic Design Codes, Equation 2-22, the vertical design basis spectral acceleration, SADV, is smaller than the horizontal component. Therefore, SADV equal to 1/2 SAD for the sites without near-fault effects. Therefore, the near-fault adjustment factor, NAD and NVD, equal to 1. If near-fault effect has to be considered, SADV equal to 2/3 of SAD. Therefore, the vertical design basis spectral acceleration is smaller than the horizontal one. And SAD is the horizontal design basis spectral acceleration. For near-fault earthquake, the vertical component is larger than the one far away from the fault. Therefore, for near-fault earthquake, the vertical component is 2/3 of the horizontal component. For far-field earthquake, the vertical component is just 1/2 of the horizontal component. According to Seismic Design Code Equation C2-10, we can determine the vertical design basis seismic force for the beam and slab. VVBS. V is the seismic force, and V here, the sub-V here, subscript V here, is the vertical component, and BS is the vertical seismic force of the beam and slab, equal to I divided by 1.4 alpha Y. I is an importance factor. Alpha Y is the first yielding seismic force amplification factor times SADV divided by FUV modification. FADV is the vertical design basis spectral acceleration. FUV is the vertical design basis seismic force reduction factor for structural system due to ductility. And WBS is the total weight of beam and slab. That's the dead load of the beam and slab. And due to soil structure interaction, the ratio between SADV and FUV is modified. If the site is far away from the fault, therefore the site is designed without consideration of the yield fault effect, then the modification can be determined by this equation. That's the seismic design code equation C2-11A. When SADV divided by FUV is less than 0.15, no modification is necessary. Therefore, the ratio after modification equal to the ratio before modification. If the ratio SADV divided by FUV is larger than 0.4, then the ratio is modified to 70% of the one before modification. In between, linear interpolation is adopted. Therefore, when SADV divided by FUV is greater than or equal to 0.15, less than or equal to 0.4, SADV divided by FUV modification equal to 0.52, SADV divided by FUV plus 0.072. If the site is near the fault, therefore near fault effect has to be considered, then the modification of ratio is given by seismic design code equation C2-11B. If the ratio is less than 0.20, no modification is necessary. Therefore, the ratio after modification equal to the ratio before modification. If the ratio is larger than or equal to 0.53, and this is modified to be 70% of the one before modification. In between, linear interpolation is adopted. The vertical design spectral acceleration of the beam and column has to be determined with the information about the fundamental vibration period of the beam and the slab. The fundamental vibration period in the vertical component of the beam and the slab can be determined by eigenanalysis or structural analysis. Another alternative, to make it more conservative, therefore the fundamental vibration period of the beam and slab in the vertical direction may be assumed to lie between 0.2 T0D and T0D, and T0D is the corner period between short period and medium to long period, in order to have maximum vertical spectral acceleration. Therefore, SADV equal to 1/2 SAD, and SAD to have the maximum value. Therefore, SAD equal to SDS for the site without near fault effect. That's the site far away from the active fault. If the site is close to the active fault, a near fault effect has to be considered. Therefore, SADV equal to 2/3 of SAD, and SAD to make it to be the maximum one. Therefore, assign SAD equal to SDS when TBS is greater than or equal to 0.2 T0D and less than or equal to T0D. And this equation is given by the seismic design code table 2-5A, SAD equal to SDS. And the vertical design basis seismic force reduction factor for the beam and the slab can be considered with the information about the fundamental vibration period of the beam and the slab. And to make it simple, the fundamental vibration period can be found from dynamic analysis of the structure or by the assumption that it lies between 0.2 T0D and 0.6 T0D, and T0D is the corner period of the between the short period and the medium to long period. If the vibration period lies between 0.20D and 0.6 T0D, then the seismic force reduction factor due to ductility can be given by the seismic design code equation 2-15, FUV equal to square root 2RA minus 1, and RA is the allowable ductility capacity. According to the seismic design code equation 2-15 and 14, for site class 1, 2, or 3, RA equal to 1 plus R minus 1 divided by 1.5. For Taipei Basin, the allowable ductility capacity RA equal to 1 plus R minus 1 divided by 2. If the beam and slab are properly designed, the ductility capacity of the beam and the slab can be assigned equal to R equal to 3.0. Therefore, once we have R, we can compute RA, and from RA, we can have the vertical seismic force reduction factor due to ductility. Once we have SADV from the previous slide and FUV from the current slide. Therefore, by applying this equation, we can compute the vertical seismic force of the beam and slab. And here's an example from our previous lecture. We know that a residential building located at Ruishui Township, Hualien County, and within 2 kilometers from Yuli Falls. The site is hard site, that is site class 1, and the question is to find vertical design basis seismic force of beam and slab, that's VVBS. From previous lectures, we have already had some information about this building. I, the importance factor, equal to 1.0, W, the total weight of the structure, equal to 146.05 ton force. And among the total weight of the structure, WBS, that's the weight of the beam and slab, equal to 126.39 ton force. And the weight of the column, WC, equal to 19.66 ton force. Alpha Y equal to 1.0. SDS, that's the design basis spectral acceleration for short period structure. SDS equal to 1.136. From seismic design code equation 2-22, for the site with near fault effect, the vertical component equal to 2/3 of the horizontal component. And SAD is assigned to be SDS in order to have the maximum, the greatest spectral acceleration. Therefore, SADV equal to 2/3 times 1.136 equal to 0.757. And the unit is G, gravitational acceleration. So far we have SADV, and the next question is to find out the seismic force reduction factor due to ductility. If the beam and column are properly designed, the ductility capacity can be assigned to be R equal to 3.0. Because the building locates at site class 1, therefore the allowable ductility capacity RA equal to 1 plus R minus 1 divided by 1.5 equal to 2.333 according to seismic design code equation 2-15. Then we can compute the vertical seismic force reduction factor due to ductility, FUV equal to square root of 2RA minus 1 equal to 1.915 according to Seismic Design Codes Equation 2-15. So far we have SADV, the vertical component of the design basis special acceleration, and FUV, the vertical seismic force reduction factor, so that we can have the ratio between SADV and FUV equal to 0.757 divided by 1.915 equal to 0.395, and it is larger than 0.2. Therefore, it has to be modified, and the modifier of the ratio equal to 0.52 times SADV divided by FUV plus 0.096 equal to 0.302, according to Seismic Design Codes Equation C2-11b. So far we have I, the importance factor, equal to 1.0, alpha Y, the first yielding amplification factor, equal to 1.0, WBS, the weight of the beam and slab, equal to 126.39 ton force, and SADV divided by FUV modification equal to 0.302. Therefore, we can determine the vertical design basis seismic force of beam and slab equal to 0.216 WBS equal to 27.26 ton force after substituting WBS into this equation. And the vertical design basis seismic force is computed according to the Seismic Design Codes Equation C2-10. So far we have determined the vertical seismic force of beam and slab, and then we move to determine the vertical seismic force of column, VVC. And according to Seismic Design Code Section 2-18, VVC equal to I divided by alpha Y, SADV divided by FUV times WC. And I is the importance factor, and alpha Y is the first yielding amplification factor. Since column axial failure may induce collapse of the structure, therefore the vertical seismic force of the column cannot be reduced due to redundance and strain hardening. So 1.4 is replaced by 1 here. For beam and slab, we have 1.4 here, but for column, 1.4 is replaced by 1.0. In addition, the ratio between SADV divided by FUV cannot be modified anymore because the column axial failure is very serious. It may induce collapse of the structure. And WC is the total weight of the column. That's the dead load of the column. In order to find out the design basis special acceleration of the column, we have to know about the fundamental vibration period of the column. Because the column is so rigid in the axial direction, so that the fundamental vibration period in the axial direction of the column can be assumed to be very close to 0. That means that it's so rigid, therefore the fundamental vibration period tends to 0. And according to Seismic Design Code Table 2-5, A, when the structure is so rigid, SAD equal to 0.4 SDS. That's the effective peak ground acceleration of the structure. Of the effective 0.4 SDS is the effective peak ground acceleration. Therefore, SADV equal to 1/2 for the site without near fault effect times SAD, and SAD equal to 0.4 SDS. Therefore, SADV for the site without near fault effect equal to 0.2 SDS. For the site with near fault effect, SADV equal to 2/3 SAD. And if the structural vibration period is very, very short, tends to 0. Therefore, the structure is very, very rigid. SAD becomes the effective peak ground acceleration equal to 0.4 SDS. Therefore, SADV for the site with near fault effect equal to 0.8 divided by 3 times SDS according to Seismic Design Codes Table 2-5A. Since the fundamental vibration period of the column in axial direction, TC tends to 0, therefore the ductility tends to 1, or the vertical seismic force reduction factor due to ductility tends to 1. Therefore, we can assign FUV equal to 1.0 according to Seismic Design Codes equation 2-15. From previous slide, we have already know about SADV, and from this slide, we have known about FUV equal to 1.0, so that we can compute vertical seismic force of the column. VVC equal to I divided by alpha y, SADV divided by FUV, and FUV equal to 1, SADV for the site without near fault effect equal to 0.2 SDS. Therefore, for the site without near fault effect, the vertical seismic force of the column equal to I divided by alpha y times 0.2 SDS times WC. WC is the weight of the column. And for the site with near fault effect, VVC equal to I divided by alpha y, and SADV equal to 0.8 divided by 3 times SDS times WC, according to Seismic Design Codes, section 2-18. And then back to the example, a residential building located at Ruishui Township, Hualien County, and within 2 kilometers from Yuli Fault, and the site is hard site, and the question is to find vertical design basis seismic force for column, that's a VVC. And VVC, according to previous slide, equal to I divided by alpha y, because this is a site with near fault effect, therefore times 0.8 divided by 3 SDS times WC equal to 0.303 WC. When WC 19.66 is substituted into this equation, VVC equal to 5.96 ton force. Therefore, the vertical design basis seismic force of the column equal to 5.96 ton force, according to Seismic Design Codes, section 2-18. Once we have the vertical design basis force, vertical design basis seismic force VV, then follow the similar procedure, we can determine the vertical maximum considered seismic force VVM and the vertical small to moderate seismic force VV star. Once we have all these 3 seismic forces, pick up the maximum one and then assign the maximum one to be the vertical design seismic force VVD. Therefore, VVD equal to maximum of VV, VVM, and VV star. Therefore, the vertical design seismic force is the maximum of design basis seismic force, maximum considered seismic force, and small to moderate seismic force. And here are the reference, Seismic Design Codes of Building, published in 2011 by the Ministry of Interior, and it can be downloaded from this website. And this is the video for Lecture 1 in English and Chinese version. Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6, Lecture 7, Lecture 8, Lecture 9, Lecture 10, Lecture 11, Lecture 12, Lecture 13, Lecture 14, and Lecture 15 This one, the videos on vertical design seismic force is under construction, is the current one. From this lecture, we have talked about vertical design seismic force. Since the fundamental vibration period in the vertical direction for the beam and slab is different from the column, therefore, the vertical design seismic force for the beam and column have to be computed separately from the column. Therefore, the vertical design seismic force of the beam and column and of the beam and slab is different from the column. We can determine the vertical design basis seismic force VV and also the vertical maximum considered seismic force VVM and the vertical small to moderate seismic force VV star by similar procedures. Once we have these three seismic forces, we pick up the maximum and assign it to be the vertical design seismic force. Therefore, the vertical design seismic force VVD is the maximum of VV, VVM, and VV star. That's all for this lecture. Thank you. See you next time. Bye-bye.